So welcome to this second course about the spectral theorem for compact self-adjoint operators. In this lecture, we will give a full example. So remember that this video is complemented with lecture notes which are essential for the understanding of this course. I assume that you have read these lecture notes and that you have also followed the first video about the statement of the spectral theorem. We will now work on an example. So our aim is to illustrate the spectral theorem, which we start with a separable Hilbert space that is infinite dimensional, an operator from H to H, which is compact and self-adjoint, and then the conclusion is that there exists an orthonormal basis of H and a real sequence that goes to 0, such that Tx is sum over k in n, lambda k, x scalar ek. In other words, T is a diagonal operator in this basis. So the difficulty we face with this theorem is that we have no characteristic polynomial to find the eigenvalues and then the eigenvectors. So one needs to develop a strategy which depends on the operator considered, hopefully on a family of operators. And this is exactly what we are going to do in the particular case of convolutions on L2 of T. So Hilbert space is therefore L2 of T, which is called the set of one-periodic measurable functions, such that the L2 norm over a period, here 0, 1, is finite. And recall that when you integrate a periodic function over a period, no matter where the period starts, you get the same result. Our operator will be the operator from L2 to L2 given by the convolution with a function h, which, remember, is integral from over a period, here 0, 1, of f of t, h of x minus t dt. H is itself a periodic function. And in this example, we will take h of t to be a Heaviside function, periodic. So it's 0 on minus 1/2, 0, 1 on 0, 1/2, 1/2 in 0 and 1/2, and 1 periodic. And it will be an exercise for you to check which properties of h we are using so that the conclusion of the spectral theorem stays valid. So the first thing, are the hypotheses satisfied? And therefore T should be self-adjoint. So we have to look at Tf scalar g, which is the integral of Tf of x, g bar of x, the complex conjugate, which is, once we replace by the definition, integral from 0, 1, integral of 0, 1 of f of t, h of x minus t dt, g bar of x dx. And then, of course, one wants to do Fubini, that is, put the g in this integral and then exchange the order of the integration, which gives us integral from 0, 1, integral of 0, 1 of f of t, h of x minus t, g bar of x, dx dt. And then we see that here f doesn't depend on x, so we put it outside the integral, which gives us integral of 0, 1 f of t, of integral of 0, 1, h of x minus t g bar of x dx dt. And what we do next is that we realize that h is real valued, therefore equal to its conjugate, so this bar goes over here, and therefore goes over the whole integral. So we get integral of 0, 1 f of t times the conjugate of integral of 0, 1, h of x minus t g of x dx, and we recognize under the complex conjugation, h convolved with g, so we get integral of 0, 1 f of t, h convolved with g of t bar, which is nothing else than the scalar product of f t g. Therefore, the adjoint of t is t itself. T is self-adjoint. You may wonder if you are allowed to use Fubini. Well, the answer is yes, thanks to Cauchy-Schwarz inequality. What we have to check is that the double integral of f of t, h of x minus t, g bar of x in modulus dx dt is finite. what we do is that, again, this f of t goes outside, and then we are left with an integral to which we apply Cauchy-Schwarz. And we have integral of 0,1 of mod f of t, integral of 0,1 of h of x minus t squared, mod squared dt to the power 1/2, norm of g2. And now here we do a simple change of variable, s equals x minus t. Therefore, we get an integral with bound depending on x, but over a full period. So we can remove this bound. And we get that this is just integral of 0,1 of f of t, norm h2, norm g2 dt, which is finite because if f is in L2, f is also in L1 of the torus, thanks to Cauchy-Schwarz again. Note that we could here have used that h is bounded and just removed h infinity outside the integral, and we would have had integral of f of t mod f of t mod g of x, and therefore it's the L1 norm of f, L1 norm of g, which is finite, thanks again to Cauchy-Schwarz, which tells us that if the L2 norm is finite, the L1 norm as well. So t is self-adjoint. So now for the compactness. Well, tf of x is of the form integral of 0,1 k of xt f of t dt, with k of xt is h of x minus t. And this looks like an integral operator. It's an integral operator, and if the kernel is square integrable, then this operator will be Hilbert-Schmidt, therefore compact. So let us look at the L2 norm of the kernel, integral of 0,1 of mod k of xt dx dt is integral of 0,1 h of x minus t mod squared dx dt. So we integrate first in x, we get the h2 norm, integral of 0,1 dt, which is of course the h2 norm of h squared, which is finite. T is therefore Hilbert-Schmidt and compact. Okay, that is hiding the difficulty in the fact that we are able to prove that Hilbert-Schmidt operators are compact, and that integral operators with square integrable kernel are Hilbert-Schmidt operators. We may as well use a compactness criterion in infinite dimension, which can be Arzela-Ascoli, which we call K is a compact metric space, X is a part of the set of continuous functions on K, then it is compact if and only if X is pointwise bounded. So f of x is bounded over all f in x for each fixed x. X is equicontinuous, that is, you write the continuity of a function, that is, there exists for every epsilon and every k, there exists an eta, which depends on x, such that the distance from x to y is less than this eta, implies that f of x minus f of y is less than epsilon. Now, equicontinuity means that this eta doesn't depend on the f of x. And the last property is that f has to be closed. So if you remove that, you just say that the closure of k is compact if and only if the two first properties are satisfied. Why are we looking at continuous functions? We are in L2 of t. Well, if k is included in C of t, continuous one-periodic, and is compact, then to start with, k is also part of L2 of t, because continuous functions are square integrable, and k is also compact in L2 of t. Why? Because if we take fn sequence in k, we can extract a subsequence that is uniformly convergent, and uniformly convergent sequences are also convergent in L2 of t. So we have extracted from fn a sequence that converges in L2 of t, therefore the set was compact. And now the observation is that as f and h are in L2 of t, f convolved with h is continuous, 0,1 or continuous for t, because it's also one periodic. 0,1 is compact, and if the L2 norm of f is less than 1, then Cauchy-Schwarz tells us that h convolved with f is less than the integral of 0,1 of mod h of x minus t squared dt to the 1/2 times the norm of f2. The first one is h2, and the second one is bounded by 1. So t of b is pointwise bounded. Well, is it equicontinuous? Well, the same reasoning, little bit more subtle. You write H convolved with F as integral of 0,1 of the translate, tau x will be the translate. H check is the reverse of H, F of t. So H check of S is H of minus S, and tau x is just the translate. And then H convolved with F minus H convolved with in x minus H convolved with F in y is just the integral of 0,1 of tau x H check minus tau y H check times F of t. You do Cauchy-Schwarz, and then you use the fact that translations are bounded, and the F here goes because we have assumed that the norm of F is less than 1. So we get equicontinuity. So T of B is compact in C of 0,1, therefore in L2 of T. So the operator T is compact. Of course, we could also have used directly L2 compactness through Kolmogorov-Riesz theorem. Recall that we have seen that a set is compact in L2 of R if and only if it is closed, bounded, equi-integrable. That means that for every epsilon positive, there exists R strictly positive, such that for all F in X, the tail of the integral of mod F squared is less than epsilon. So this holds for every single F in L2, and here what has to be, it has to be uniformly F in X. And of course, we are only looking for functions which are, we can see L2 of T as functions in L2 of over a single period 0, 1. So this condition doesn't make sense there. And the last condition is that translations are equicontinuous, which I will recall here. So in L2 of T, this reduces to X closed, X bounded, and translations are equicontinuous. And now checking these conditions is done exactly in the same way. So we have 3 ways to see that T is compact. But that just tells us that the spectral theorem is valid. Now we have to find eigenvectors and eigenvalues. And when we speak about convolution, Fourier can be very far. We have the exponentials, ek of t is e2 I pi kt, and what our course about Fourier series tells us is that this is an orthonormal basis of L2 of t. Further, H convolved with ek, a simple computation, tells us that it is integral of H of t e2 I pi kx minus t dt, and then the exponential splits in 2 parts. So we have integral of 0, 1 ht e to the minus 2 I pi k t dt, and the exponential in x goes outside the integral. And we see that this is ck of h, the Fourier coefficient of h, times ek. In other words, ek is an eigenvector of t with eigenvalue ck of h. And a simple computation that I leave as an exercise shows that ck of h is 1/2 if k is 0, 0 if k is even, and 1 over I k pi if k is odd. So what do we now have? Tf of x is sum of k and z, ck h, f scalar ek, that is just what the spectral theorem tells us. F scalar ek is ck of f, so we can rewrite this as sum over k of ckh, ckf, ek. In other words, it's 1/2 of c0f plus sum over p in z, 1 over I, 2p plus 1 pi, because only the odd ones come into the game, c 2p plus 1f, e 2I pi, 2p plus 1 of x. Of course, we have only used the spectral theorem in a mild way, and we could obtain this expression directly by saying that the case Fourier coefficient of h convolved with f is ck of h times ck of f. And that's all for this lecture. Thank you for your attention. In the next video, we will give the key tools that will appear in the proof of the spectral theorem, and we call that my notes are available on my webpage.